This is hopeless. What's game theory? I don't understand how it works.
What do you mean you don't understand how it works?
I just don't get it.
Everyone can understand game theory.
Who are you?
I'm the game god, here to teach you about game theory.
Well, what is it?
Glad you asked. Game theory is the study of strategic decision making between rational entities.
Huh?
In layman's terms, it's the math of decision making.
That's cool and all, but what about these other terms? Players, payoffs, extended forms?
Fear not, I have the answer to those too. Every game consists of players, strategies, and respective payoffs. The players of a game are the participants. The strategies are the actions that they take. The payoffs are the rewards they get relative to strategies that they and other players take. The game is simply the field of players, their strategies, and the possible payoffs that result from combinations of strategies.
So how are these games mathematically represented?
I'll show you. A normal form game is represented by a table. Each axis has the player and their respective strategies. Player 1, player 2 use 3 strategies. Each intersection in the cell represents the respective payoffs for both player 1 and player 2.
This is more boring than my book. Show me how it applies to my life.
Time for a journey.
Where are we?
You're at Sean's house.
Who's Sean?
You and Sean in this reality are con artists who've been on the run from the police.
What kind of cons do we do?
You guys have done illegal auctions, gambling activities, the whole shebang. These aren't your normal games though. The cons you guys do are based on game theory.
How do we use game theory in our scams? Where'd he go?
Time to make some money off some suckers.
Sure.
Sean and Casey's scams are based off the Monty Hall Problem. Step right up, give me a 20 and you can double your money!
Sounds good, man.
In the Monty Hall Problem, there are 3 concealed items, 2 relatively worthless items, and 1 valuable. The locations of which the player is unaware. The player then proceeds to pick one of the items.
That one.
After the player picks, the host will reveal the location of one of the worthless items. The host then offers the player to switch.
I'm gonna go with my gut. No, I'm stay with my one.
Are you sure? You have a 50-50 either way.
Strangely, contestants who switch see their odds of winning increase from 1/3 to 2/3. Yet, refrain from doing so because they think they now have a 50-50 chance, therefore, they don't switch and only win 1/3 of the time.
I'm still going with my gut. I'm staying on that one.
Ooh. Everyone's a winner!
How is this possible? Switching locations would cause you to lose if and only if you had initially picked the right one. The chances of this occurring are 1 in 3. Therefore, the probability of losing after switching is 1 in 3. So the probability of winning after switching is 2 in 3. To understand this from another perspective, switching will always cause you to win if you had initially picked a dud. The chances of this occurring are 2 in 3. Hence, the chances of winning by switching are 2 in 3. People are easily fooled by this because after the host reveals the dud, they are given the illusion of a 50-50 chance at winning, and are therefore indifferent to switching.
Ah, step right up! Give us $20 and we'll double your...
You two are under arrest.
money.
Officer, I didn't... What are you doing here?
I'm your police officer. You're in the prisoner's dilemma.
What is the prisoner's dilemma?
You and Sean have been arrested, but the police can only nail you two for an illegal dollar auction, which is punishable by 1 month in jail. They don't have enough evidence to nail you for an illegal street scam, which would be 12 months in jail. So they're using the prisoner's dilemma. If you talk and Sean stays silent, you can go free and he'll spend 12 months in jail. If he talks and you stay silent, you'll spend 12 months in jail and he can go free. If both of you talk, you'll spend 8 months in jail. If both of you stay silent, we can only nail you for dollar auction, so you'll both spend 1 month in jail. I've already told the same information to Sean. You'll have 5 minutes before your next interrogation.
If Sean stays silent and Casey confesses, Sean will get 12 months and Casey will go free. And vice versa. If Sean and Casey both confess, they both serve 8 months. If Sean and Casey both stay silent, they both serve only 1 month. If we consider the game from Sean's view, regardless of whether Casey talks or not, his best option is to confess. If Casey stays silent, Sean's best bet is to confess and serve 0 months in jail rather than 1 month. If Casey confesses, Sean's best bet is still to confess rather than staying silent to serve 12 months in jail.
The strategy that benefits a player regardless of their opponent's choice is known as a dominant strategy. In this case, the dominant strategy is for both players to confess.
The prisoner's dilemma is unique in that while the dominant strategy of the individual is to confess, both players will mutually benefit more if they remain silent. Nope, I'm not saying anything.
Yes, me and Sean were involved in the street scam.
Alright, looks like 12 months for you, Sean. Alright, you're free to go. Good to see you got out.
Weren't you just a prison guard?
I can be what I want to be. I'm the game god, remember?
Alright, whatever. Are we almost done?
Not quite. We still have to go to an African tribe.
What's happening out here?
What you have here are 2 princes fighting for inheritance of their dad's throne. This isn't your ordinary battle, though. This is a game of chicken.
What's chicken?
I'll show you.
The 2 princes will fight for the throne through the chicken game.
In this game, 2 players will run at each other with spears until either one surrenders or they collide.
If one prince charges and the other one yields, the one who charges will be given the throne.
You are king.
And vice versa.
You, my son, are king.
If both princes yield, however, no one gets the throne. If both princes charge, they will impale and kill each other, and clearly neither of them will receive the throne.
My sons.
My sons!
When looked at from player 1's perspective, one can see that the loss incurred from yielding is far less than that of colliding. Therefore, player 1's rational decision should be to yield. Knowing this, player 2's best option is to continue charging and win. However, player 1 would go through the same thought process and also arrive at the conclusion that charging would produce a victory. It is for this reason that the chicken game has no definite solution.
Wow, that was some showdown. What's gonna happen to those 2 princes?
Doesn't really matter. Let's go see an application of game theory to hunting.
The tribesmen will hunt based on the Stag Hunt game. In the Stag Hunt game, one can choose to either hunt the stag or the hare. Hunting the stag requires complete cooperation, since it takes 2 spears to kill the stag. It only takes 1 spear to kill the hare. If player 1 kills the hare, and the second player goes for the stag, only player 1 will receive the hare, while player 2 will fail to kill the stag. The inverse applies if player 2 goes for the hare and player 1 goes for the stag. Player 1 will fail and receive nothing. If both players go for the hare, they will have wasted their spears and will be rewarded with a relatively smaller prize. If both players cooperate and go for the stag, they will receive the greatest available reward. However, the dilemma arises in that each player must decide independently and trust that the other player wait for the stag instead of wasting spear on the hare.
If one player were to waste a spear on the hare, the other player would both be deprived of the hare and the stag, since it takes 2 spears to kill a stag. After successfully hunting the stag, the 2 tribesmen take it to a butcher, where they receive 100 gold coins. They must now decide how to split the coins amongst their fellow tribesmen.
So how are the tribesmen going to split the money?
With the pirate game. In the pirate game, there are 5 rational pirates, A, B, C, D, and E, who find 100 gold coins and must decide how to distribute them. The pirates have a strict order of seniority. A is above B is above C is above D, and D is above E. The pirates' rules of distribution are these. The most senior pirate proposes the distribution of coins. Then all the pirates, including the proposer, vote on whether or not to accept or decline this distribution. If it is approved by a majority, or if it is a tie vote, the distribution will occur. If not, the proposer is thrown overboard, and the next most senior pirate makes a new proposal to begin the system again. The pirates base their decisions on 3 assumptions. Firstly, each pirate wants to survive. Secondly, each pirate wants to maximize the amount of gold he receives. Lastly, with all else equal, each pirate would prefer to throw another overboard to increase the amount of money they have. Although this is called the pirates game, for the sake of this narrative, we will equate pirates with tribesmen. One would expect that Pirate A would give the least amount to himself in order to avoid being thrown off the ship. However, this is far from the actual result.
We can find the solution by using backwards induction, where we start at the end of the game and logically backtrack to produce a winning first move.
If one works backwards through backward induction and assumes that D and E are the only 2 left on board, D would propose 100 for himself and none for E. The tie vote would allow D to both stay alive and maximize the coins. Knowing this, Pirate C would only have to offer E 1 coin and keep 99 for himself. Since E would have originally gotten none in the original transaction, E will side with C, and this 2-man vote will keep D in the minority and C on the ship. B only has to offer D, therefore 1 coin, and keep 99 for himself, knowing that D would have received 0 in the previous transaction. The 2-man vote of B and D ties the 2-man vote of C and E. Knowing this, A only has to give C and E 1 coin each and keep 98 for himself. The 3-man vote of A, C, and E will overrule that of B and D, allowing A to both stay on the ship and keep the most amount of coins.
You mean one tribesman gets 98 coins to himself? That doesn't seem very fair.
Game theory is not fair. Get over it. Hopefully this adventure has shown you that game theory has many applications in the real world. Now, get back to your textbook with a new attitude on this wonderful branch of mathematics. Game God, out!
I didn't know there was so much game theory behind such normal decisions.